We'll cover some quick information on the frictional force. This will be real fast. Equation for friction. We'll typically see FF, or a scripty F, is equal to Fn mu, Fn being the normal force. So if we're on a flat surface, if we have an object sitting here, remember our normal force is directed straight up, perpendicular to the surface an object's in contact with, and it should be equal in magnitude to the weight of the object, so that Fg equals Fn. And if we want to calculate the frictional force as we're sliding something, so let's say we're pulling this direction with some force and we have motion, let's say the block is moving to the right, we have a frictional force holding it back that's equal to the normal force, Fn times mu. What mu is a coefficient of friction. There's a static coefficient of friction and a kinetic coefficient of friction that differ just slightly on most surfaces based on whether the object is static, sitting still, or moving. Typically we don't worry too much about that other than it's a different number. But in this case our object is moving, so we would be looking at a coefficient of kinetic friction here. And we would calculate that based on the normal force, which is of course equal to the weight of the object, that's equal to mg. Now, if this were at an angle instead, our frictional force decreases because our normal force decreases. Okay, so let's say it is still accelerating up the ramp with some kind of a force that's pulling it. And so we have motion this way up the ramp. And again, we're being held back by a frictional force that's down here. And the frictional force, again, is calculated, the maximum frictional force, by Fn times mu. Now, the normal force in this case is not equal to the weight of the object, because the weight of the object, of course, Fg, that's equal to mg, is straight down. The normal force now is perpendicular to the surface, is in this direction. It's going to be less than the weight because the surface is now tilted. And it should be equal in magnitude to the component of the gravitational force that we would call Fg or mgy. Okay, so there's our gravitational component, so that we can say that the force of friction is equal to mg, if we know this angle theta, is equal to mg cosine theta times mu. Mg cosine theta being the equation for this component of the gravitational force mg. Okay? Now, this is, of course, if it's moving. Oftentimes, one of the conceptual questions you'll get is how much is the coefficient, or what's the frictional force when it's not moving? And I'll have students calculate it this way, which is incorrect. The correct, the simplest example of that is if we have the object laying flat. If I had the object laying flat and it wasn't moving, and I said, well, how much is the frictional force if there's no pull on it? You would say, well, the frictional force is 0. Fg here and Fn. You say, well, the frictional force is 0. Well, what if I pull with 2 newtons and it doesn't move? Well, then what's the frictional force have to be over here? Well, the frictional force also has to equal 2 newtons because it's at equilibrium. It's not sliding. Well, if I pull it with 3 newtons then, and it still doesn't move, well, then the frictional force is 3. And what if I stop pulling? Then the frictional force also doesn't exist because it's not going to all of a sudden slide backwards when you stop pulling. So the same thing's true on an angled surface. Okay? Once I reach a point, though, let's say I pull with Fp where it equals 4 newtons, and then it does start to accelerate. Okay? Now we have a case of where I don't know how much the frictional force is, but it's probably less than 4 newtons, and it has to be less than 4 newtons for it to start moving. Now we need to look at it and say, well, how is it moving? Is it moving at constant velocity, or is it accelerating? Okay, once we get it to move, if it moves at constant velocity, okay, that means we've reduced our pull and we're matching friction again. So we have to overcome friction to get it to move and accelerate because there has to be a net force. In other words, the push or the pull has to be greater than the friction. But once it moves, if it moves at constant velocity, then we know net force is 0 and that the frictional force is equal to the pull in the opposite direction as it's moving at constant velocity. On an angled surface, same thing is true. if we're wanting to calculate, or if we're wanting to know something about the frictional force, let's say it's a book sitting on a ramp, and it's not sliding. If it's not sliding, again, we want to make sure we are not calculating the frictional force. It is now upward. We want to make sure we are not calculating the frictional force as being equal to Fn mu. And why not? Well, this equation tells us the maximum frictional force. Okay? And again, if I lay my ramp flat, there is no frictional force. And if it's not sliding, what it tells me is that this component of the force that's here, mg, refer to this as mgx and mgy. What it tells me is that the component of the gravitational force down the ramp, mgx, is not great enough to overcome the maximum amount of friction. So if I know the maximum amount of friction possible, let's say is 20 newtons, then I don't know what my frictional force is here, and I don't know what my mgx is, but I know my mgx is not greater than 20 newtons. Let's say mgx is 15, and this thing's not sliding. How much is my friction? Well, it's 15. And what if I increase so mgx is, maybe I'm going to make this a little heavier, I'm going to add some weights to it. That increases mg and therefore increases mgx. Let's say this is 18 and it's not sliding. Then my frictional force is 18. And then when I reach something that's greater than 20 for my mgx, it will begin to slide. And then we do calculate friction this way, but we're going to switch from the static coefficient to the K, UK, kinetic coefficient. We'll talk about how that frictional force decreases when we go from motion, non-motion to motion in the next section.